Hey y'all, welcome back. On tonight's homework, we're going to be looking at some tangent line approximations and using what we know about the second derivative to determine whether or not an approximation is an over or underestimate compared to the actual value. So we'll start this homework off with some review here of explicit differentiation. This is the kind of differentiation we used in units 2 and 3. So we're basically just going to be using the chain rule here. So the derivative of cosine is sine. So this is going to be, negative sine. Negative sine of 3x squared times the derivative of 3x squared, which is going to be 6x. Part B says 2 times sine of natural log x. So we'll start by differentiating 2 sine x, which would be 2 cosine x. Try to fit that in there. So 2 cosine of the natural log of x times the derivative of natural log of x, which is 1 over x. C, we're going to start with the power rule. 4 times 5x plus 6 to the third power times the derivative of the inside, which is just 5. For D, we've got the natural log of something. So the derivative is going to be 1 over that something times the derivative of that something, which would be 3x squared plus 6. Now, usually on these natural log derivatives, like on B and D, if it's a multiple choice item, then these are going to be simplified so that like this thing, this 3x squared plus 6 will be in the numerator. Just keep that in mind. We can leave it like this for now, though. Letter E, the derivative of secant. It's been a little while since we did a secant derivative, but the derivative of secant is secant times tangent. So we're going to have secant of e to the 4x times tangent of e to the 4x times the derivative of e to the 4x. And we're actually going to have to continue using the chain rule here. The derivative of e to anything is just e to anything times the derivative of that anything. So we have e to the 4x times 4. For f, we're going to differentiate tangent of 7x, all that to the 5th power. So our outside function here is going to be something to the 5th power. So we'll use power rule there. 5 times tangent to the 4th power of 7x times the derivative of tangent. And the derivative of tangent is secant squared. So secant squared of 7x times the derivative of 7x, which is 7. Now here's another case where you could consider doing a little bit of simplifying here. Rewriting 7 times 5 is 35, but honestly, I'm just fine with you leaving it like that. Okay, number 2, it says let f be a function that's differentiable for all real numbers. The table below gives the values of f and the derivative of f prime for selected values or selected points x on the closed interval from negative 1.5 to 1.5. The second derivative of f has the property that f double prime is positive, okay, on this interval. Now, just as a little reminder, the significance of f double prime being positive means that f is concave up, meaning the graph, at least if we exaggerate it, will do something like this. Okay, so let's see what the question is actually going to ask us here. It says, write the equation of the tangent line to the graph at f, or of f, at the point where x equals 1. Okay, so we're writing the equation of a tangent line. So we're going to need a point, and we're going to need a slope. This point is 1 comma something, and we can get the something, since we don't actually know what the equation is, from the table, where x is 1, y is negative 4. So the y coordinate here is negative 4. And the slope is going to be the slope at that x value. The slope here is going to be 5. So now we can write the equation of the tangent line. Y plus 4 equals 5 times x minus 1. B says use this line to approximate the value of f of 1.2. So we're just going to substitute in 1.2 into x. and simplify this. Okay, maybe I'll move this over so I have a little bit more space here. So y plus 4 equals, let's see, 1.2 minus 1 is going to be 0.2. 0.2 times 5 is going to be 1. So get y plus 4 equals 1. So y should be negative 3. So this is our approximation. Just to be clear, this is our approximation. And so if we want to find the value of f of 1.2, we don't have that in the table, so we can't say precisely what it is. But what we can say is that it's approximately negative 3. C says, is this approximation greater than or less than the actual value? Give a reason for your answer. So to determine whether or not you have an overestimate or an underestimate depends on whether or not your graph is concave up or concave down. If it's concave up, like in this case, then the tangent line is going to be below the curve, and in which case the approximation will be an underestimate. Okay, so in other words, the approximation would be less than the original. Okay, it's an underestimate. However, if the graph is concave down, then the tangent line will be above it and therefore be an overestimate. And so the estimate, maybe I don't want to write too much on here and make it confusing, but the estimate will be an overestimate. So C is saying it's greater, what's going on at 1.2? It said in the problem that f double prime was positive. So we know it's concave up. So that means our tangent line will be below it. So we're going to say that the approximation is less than the actual value. Okay? In other words, we can say that f of 1.2 is going to be greater than negative 3. Okay, now our reason for this is because f double prime is positive, and therefore concave up. Okay, so this is really our answer. Approximation is less than the actual value, and the reason is because f double prime is positive. Okay, let's take a look at number 3. It says for each of the following determine y prime. So we're just continuing to practice some implicit differentiation here. And so we'll start with A, and we're going to differentiate both sides. So the derivative of x to the fourth, which with respect to x is going to be, using the power rule, 4x cubed. And then we could do something very similar with the y, although we're going to treat y like it's a function of x, and multiply this by the derivative of y. Using the chain rule. The derivative of any constant is 0. And so if we want to solve for that y prime, we need to first move the 4x cubed over to the right-hand side by subtracting 4x cubed. And then we could divide both sides by 3x squared to get negative 4x cubed divided by 3x squared. B will be solved similarly. We'll start by differentiating both sides. The derivative of cosine is negative sine, but we got to use chain rule here, so we got to multiply by the derivative of y, which is y prime, plus, using the power rule, we'll have 20x to the fourth equals 8 plus 2y times y prime. So what I really need to do here is try to isolate my y prime. By bringing all the terms that have y prime over to the left. So I've got two of them, this one with the sign and this other one over here. So I'm going to have negative sine y prime, minus 2y y prime equals 8 minus 20x to the fourth. Now I'm going to isolate y prime by factoring out y prime, like it's a GCF, or greatest common factor. And then finally, I'm going to divide everything by what's inside the parentheses here. So I get 8 minus 20x to the fourth over negative sine y minus 2y. Let me space that out a little bit, make it easier to read. Negative sine y minus 2y. And there you go. Number 4 says the table below shows some values of the differentiable functions f and g and their derivatives. It also defines h as a third function here as f of g of x. A says determine the equation of the line tangent to the graph of h at x equals 5. Okay, so our setup here is we need a point. It's going to be 5 comma something. We need a slope. Let's start with the point. So we know it's going to be 5 comma something. And so what we need is the y coordinate of that point. So we need h of 5. So h of 5 will be f of g of 5. So first we'll evaluate g of 5. We can find g of 5 in the table right here. It's 4. So this is going to equal f of 4. And we can find f of 4 in the table as well. F of 4 is 6. So h of 5 is 6. So the y coordinate of the point is 6. To find the slope, we want the derivative of h prime, or of h, which is h prime. So h prime is going to be, just using the chain rule directly here, f prime of g times g prime. So if we want the slope at 5 specifically, we're going to evaluate f prime of g of 5 times g prime 5. G of 5 is 4. We established that earlier. So we have f prime of 4 times the derivative of g at 5, which you can see is right here at 9. F prime 4, we can find that in the table right here. It's negative 3. So h prime 5 is going to be negative 3 times 9, which is negative 27. Okay, this is going to be the slope of h at x equals 5. So our slope is negative 27. My point is 5 comma 6. So the equation of the line is going to be y minus 6 equals negative 27 times x minus 5. If we're going to use this equation to approximate the value of h of 5.1, we don't have h of 5.1. There's no 5.1 is in our x list over here, so we wouldn't be able to use the table. But we can use this tangent line to approximate it. So we'll plug in 5.1 into x, into our tangent line, and just start solving for y here. So y minus 6 equals negative 27 times 0.1. So that'd be y minus 6 equals negative 2.7. If I add 6 to both sides, I'm going to get y equals 4 point, wait a minute, no. 6 minus 2.7 would be 3.3. So so what we could say then is that h of 5.1 is approximately 3.3. Now, this doesn't ask us whether or not this is going to be an over or under approximation, but we would find that by finding the second derivative of h. I'm not going to go through that. And if we find that the second derivative of h is positive, then we know this would be an underestimate. If the second derivative was negative, the function would be concave down, in which case the approximation would be an overestimate. So just want to review that little thing there. Number 5 says, if we've got this equation, use the tangent line of the graph to estimate the y value when x is negative 0.5. So if I plug in negative 0.5 into here and here, you can see how it might be pretty difficult to solve for y. And so instead, we're going to use a tangent line approximation. So what we need for that tangent line approximation is we need a point and a slope. Starting to see a pattern here? The point is going to be at -1, 2, but we need the slope. We need the y prime, or the dy dx. I've written a lot of y primes in this homework, so I think I'm going to try a dy dx. So let's differentiate implicitly this equation. We need to use product rule on this first one. So I get 2xy plus x squared times dy dx minus 3, right? Derivative of -3x is -3, equals 3y squared times dy dx minus 0. Okay, the derivative of any constant is going to be 0. So if I'm trying to solve for dy dx, I'm going to move all the terms that have dy dx to the left-hand side, and all the terms that don't have dy dx, I'm going to move to the right-hand side. Oops, sorry, not minus x squared, not sure what I'm doing there, plus 3. So now to isolate dy dx, I'm going to factor it out as though it's a greatest common factor. And then I'm going to divide both sides by the x squared minus 3y squared. Okay, so now I got a formula for the slope. And so now to find the slope at -1, 2, so I want to find dy dx at the point -1, 2. I'm going to substitute in -1 for x and 2 for y. So I'm going to have -2 times -1 times 2 plus 3 all over -1 squared minus 3 times 2 squared, which would be -4 plus 3 is -1. No, hold up. That's +4 plus 3 is 7. And then we've got 1 minus 12 is -11. So I get -7/11. So now I know my slope is -7/11. So I can write an equation for the tangent line. Y minus 2 equals -7/11 times x minus 1, or plus 1. Okay, so I want to use this equation to estimate the y value when x is -0.5. Okay, so I'm going to plug in -0.5 into x. -0.5 plus 1 is 1/2. So 1/2 times -7/11 is going to be -7/22. And then if I add 2 to both sides, here, I guess I'll have to write this one out. 2 as a fraction with a denominator of 22. In other words, we're finding a common denominator here. Would be 44/22 minus 7/22 is going to give me, what would that be, 37/22. So what we can say is that this 37/22 is an estimate of the y value when x is -0.5. So that's our answer. Okay, number 6. It says on the interval 2, 3, what's going on with this curve? Is it decreasing concave down, decreasing concave up? So this is a little review from the last unit where we used the first and second derivative to determine intervals of increasing, decreasing, and concavity. So let's find the first derivative, just using explicit differentiation here. The old stuff, 3x squared minus 12x plus 9. So I'm just looking on this interval 2 to 3, so I'm assuming it's going to be the same between that interval, so I'm just going to pick a number between 2 and 3, like 2.5, and plug that into x and find out if that first derivative is positive or negative. So y prime at x equals, let's say, 2.5 will be 3 times 2.5 squared minus 12 times 2.5 plus 9. Now, I don't really care exactly what this equals. I just care if it's positive or negative. So we might have to, simplify this a little bit. 2.5 squared is the same thing as like 2.5 times itself. So 25 times 25 is 625. So 2.5 squared would be 6.25. So we've got 3 times 6.25 minus, 12 times 2.5 would be 30 plus 9. Okay, the last thing to do is I want to multiply this 3 times 6.25. 3 times 6 is 18. 3 times 0.25 is 0.75, so it should be 18.75. So 18.75 minus 30 plus 9, I'm not even going to bother adding these up, but what I know is that this is going to be negative because 9 and 18 is not going to add up to 30. And since I'm subtracting 30 here, I know that y prime is going to be negative on the interval 2, 3. Okay, since y prime is negative, that tells me that y is decreasing. Okay, so it's definitely going to be decreasing, which allows us to eliminate C or D. The justification for the decreasing is that y prime is negative. And so now let's check the concavity. And we can do that with the second derivative. So we found the first derivative up here. And so we're going to differentiate that again. But well, that's it. Yeah, we're going to differentiate that again. So y double prime would be 6x minus 12. And I want to know what's going on at 2.5. So if I plug in 2.5 into here, I'm going to find y double prime at that x value. And you don't have to pick 2.5. Just pick any number between 2 and 3 will do. So we've got 6 times 2.5 minus 12. Now 6 times 2 is 12. So 6 times 2.5, even if you don't know exactly what that equals, you know it's got to be bigger than 12. Okay, if you want to know exactly what it is, 15. So 15 minus 12 is going to be positive. So y double prime is positive on the interval 2, 3, which indicates that y is concave up. And so our answer here is B. We know it's decreasing because the first derivative is negative, and we know it's concave up because the second derivative is positive. Number 7 gives us the solutions to a differential equation. A differential equation, by the way, is just an equation for the first derivative. That's why it's called a differential equation. dy dx is x times y cubed. And we're going to let y be f of x. And we have a point on this function, 3, 2. So this just means we have a point at 3, 2. A says write an equation for the line tangent to the graph at x equals 3. Okay, well, we know the point at x equals 3, so that's kind of nice. We know our point is 3, 2. And so what we need is the slope, which we're going to find with the derivative. Now, check this out. We already have the equation for the derivative. We don't need to find the second derivative. So dy dx at the point 3, 2 is going to equal 3 times 2 cubed. So this would be 3 times 8, which is 24. So my slope is 24, and I'm ready to write my equation. Y minus 2 equals 24 times x minus 3. B says use the tangent line equation from part A to approximate f of 3.1. So we'll plug in 3.1 into x. 3.1 minus 3 is going to be 0.1. 1/10 of 24 is 2.4. If I add 2 to both sides, I'm going to get y equals 4.4. So we'll say that f of 3.1 is approximately 4.4. C says find the second derivative in terms of x and y. Then, given that y is positive and x is positive in this interval, determine whether or not the answer in part B is an over or under approximation. So let's find that second derivative. Okay, so going back to the original equation, what was that? dy, I'll just rewrite it here so I don't have to keep scrolling up and down, was x times y cubed. Okay, so if I'm going to differentiate both sides with respect to x, I'm going to end up with the second derivative equals, and I'm going to have to use a product rule here. So f prime g is going to be derivative of x is 1 times y cubed plus x times 3y squared times dy dx. Okay, now here's the tricky part. It says determine it in terms of x and y. So I don't really want a dy dx in my equation. I want to get rid of that. This thing right here. I just want it in terms of x and y. The good news is we already know what dy dx is in terms of x and y. We have that as the equation that was given initially. So we can make a replacement here and say that the second derivative equals y cubed. I'm going to drop the 1 here. I'm going to move that 3 out to the front. And then times xy cubed, because that is dy dx. So the second derivative is going to equal y cubed plus 3x squared y to the 5th. Okay, now in order to determine whether our answer in part B is an over or underestimate, we need to know whether or not the second derivative is positive or negative, so we can check the concavity. Now it says that y on the interval y 3 to 3.1, y is positive and so is x. So looking at this equation for the second derivative, this y cubed is going to be positive, x squared y cubed, but all those are positive numbers. So this whole thing's positive, so maybe I'll just write it like this. Since y is positive and x is positive on the interval 3 to 3.1, the second derivative is positive on that interval. And being that the second derivative is positive, that means that the original equation, which is, what are we calling it? F, I guess. So the curve is concave up. I'll just say there. I'm trying to be as brief as possible. The curve is concave up. So since it's concave up, that means our tangent line is going to be below it. So I'll say, therefore, what was our answer in part B? 4.4. Therefore, 4.4 is an under approximation because the tangent line is under the curve. I'll move all this text up a little bit. All right. Well, I think that about wraps it up for this homework. Thanks, y'all, for watching. I hope you are understanding these tangent line approximation problems a little bit better at this point. As always, if you have any questions, please reach out and I'll be happy to help you. Y'all have a great night. I'll see you next time.